Hello guys, welcome to the DMS online school. In today's video we are going to revise science paper 1, which reads examinations Council of Zambia, examination for school certificate ordinary level science paper 1, 10th November 2023. So this is the paper which was written by the grade 12s internal for last year. Alright, so if you are new to this channel, you are most welcome, and on this channel I revise past examination paper and also teach online lessons for science, biology, civic education, English, mathematics, and RE. So if you're new to this channel, you are most welcome. If you haven't considered subscribed, or if you haven't subscribed, please consider clicking on the red subscribe button below so that whenever I upload a new video, YouTube will be able to notify you so that you don't miss any upload on my channel. All right, without further ado, let's go straight into this revision. All right, so this is section A. Section A consists of 20 multiple choice questions in which you have just to choose the best answer by just making a cross or a selection. All right, so this is A1, and the question reads: the following diagram shows a pendulum that moved from A through B to C and back to B in 1.2 seconds. So this is a pendulum, and then it has to swing from A through B to C and then back to B. Then the question says, what is the period of oscillation of the pendulum? So they want the period of oscillation of the pendulum. Now for you to be able to answer this question, you must understand what the period of oscillation is. So this is the definition. So by definition, period is time taken to make a complete oscillation or swing. So the time that it can take, if this one was to swing from A to C and then back to A, that time that would elapse is what we call the period. So to be able to answer this question, it's simple to use this formula as well, where we know that period, which is capital T, is equal to time t, small letter t, of N, which is the number of swings. Okay, so we have been given time, so we just have to substitute. So T is period, which we are asked to find. So we'll just say T is equal to, where T is, which is time, 1.2 seconds here, you place it there, over, then N is the number of swings. Like if this bob of, or the pendulum had to move from A to C and then back to A, we'll consider that one swing or one oscillation. Now it had to move from A to B. This is considered as a quarter oscillation, and then from again B to C, another quarter oscillation. So from A to C, that would be half oscillation. Then it had again to come to B, so this was again from C to B, a quarter oscillation. Okay, so in other words, it made a half from A to B, to C. Then from C to B, it made a quarter. So a half and a quarter gives us what we call 3/4, which is in 3/4. Okay, it moved 1, 2, and then 3. This one should have been, if it went back there, it would have been 4. Now it just moved 1, 2, 3. So it is 3/4 oscillations. Now, these oscillations, we are supposed to write here N, which is 3/4. Now I can't write it in this way, so I had just to convert it in this way. So this is how I converted it. Let me just get my calculator and show you how I did it. So I just got like 3, like that, then divided by 4, then I said equals, which is 0.75. So we have converted this one into 0.75. So here I had to put 0.75, and I say equals, then I'll divide 1.2 divided by 0.75. I got 1.6 seconds. So this is our period of oscillation, meaning that our answer is D here. So this is our answer, D. So let's move to question 2 here. So question 2 reads: a bomb was dropped from a plane that was flying 2.0 kilometers above the ground at a speed of 900 kilometers per hour. Ignoring air resistance, take G, which is acceleration due to gravity, to be 10 meters per second square. how long did it take the bomb to strike the ground? Okay, so we have a plane that is moving, and then it drops a bomb, and then that bomb, the plane was actually flying at 200 kilometers above the ground, and then it was moving at that speed horizontally. You know, it is moving horizontally like that at that speed, but from the ground to where the plane was, it is 2.0 kilometers. Now I must tell you that this speed, since it is horizontal, and then the bomb, once it is dropped, it falls down like that, we consider vertical movement, so we'll ignore this speed here. We ignore it. All right, so we are going to ignore it. So since they're saying how long did it take the bomb to strike the ground, so how long is time. If they say how far, it is distance. So how long, the best formula that can help us to find this question is this one here, which involves time. So AC distance is equal to u times t plus half gt squared. So AC is distance, u is initial velocity, t is time, and then g is acceleration due to gravity, t is time here. So we can substitute c is distance. We have been given 2.0 kilometers. So this distance changes to meters by multiplying it by 1000. So this, when you multiply 2.0 by 1000, it will be 2000 meters. So here it will be 2000 meters as distance is equal to, then you know, if a stone was dropped and then it started moving downward, we can consider that point it started moving downward to have actually zero velocity, because it is moving downward and then not vertical. I mean, it is moving vertically downward, not horizontally. This can confuse you by thinking that maybe this one is a initial velocity, but no, it's not initial velocity, because the plane is moving this way, then the stone is dropping that way. So as far as vertical speed is concerned, at that point it was dropped, it was at 0 in as far as vertical velocity is concerned. So here your initial velocity will be 0 times time, which is t, then plus, then half times c, then acceleration due to gravity g is 10 meters per second, then times t. T is unknown, that's why we are just putting t squared, because they're saying how long did it take. Then we'll say, okay, 2000 is equal to 0 times t, it will be just 0, so that 0 we ignore it. Then here we said 1 over 2 times 10, which will be actually 5. So what happened here was this. So let me just show you what had happened in this case. So in this case, if you multiply 1 over 2 times 10, it will give you 5. Why? Because 1 over 2 is just 0.5. So this 0.5 again times 10, okay, it will give you 5, that one here. So 5 times t, it will be just t squared like that. Okay, now remember we are looking for t, not 5, so divide by 5. Also here we divide by 5, so 5 into 5 it will go. Okay, then 5 into 2000, it will be actually 400 equals, so 5 into 5 it will cancel, will just remain with t. Now we are looking for t, not t squared. So to get rid of the square, or square root this side and also this side, so that if we square root 400, we'll have 20, and then the square root of here, this square and the square root will cancel, will remain with t. So t is actually 20 seconds. So our answer will be B there, if not mistaken. Remember guys, I can also make mistakes as a human being, so it is very well that you do the right thing by making sure that you check with other books available there. Okay, so if you're enjoying already, please give this video a like and let me know in the comment section, and consider also subscribing. All right, so let's go to question 3, which reads the diagram, the following diagram shows a uniform 4-meter wooden rod pivoted at its midpoint. 4 forces are acting on the rod to keep it in equilibrium. Okay, so we have this wooden uniform rod, okay, which is from here up to here. They're telling us it is 4 meters, and then it is pivoted at its midpoint. So it is pivoted here. This is the pivot on this midpoint here. So this is the midpoint, meaning from here up to here it is 2 meters, then from here up to there it is 2 meters. Then they're saying 4 forces are acting on the rod to keep it in equilibrium. So to keep it in equilibrium is the same as keeping it in balance, so that it does not fall this way or the other way. So their forces, how many are they? We have this force F here, we have this force of 20 Newton here, we have the 30 Newton force here, and also the 30 Newton and the 20 Newton force there. And then the question says, what is the force F here? So they want this force F here. Okay, so this is the force they want, right? So if this is in equilibrium, this one here, then we can use the principle of moment. So the principle of moment for an object in equilibrium states that the clockwise moment is equal to the anticlockwise moment, or anticlockwise moment is equal to clockwise moment. So let me show you what it is in terms of a formula. So if I say M stands for moment and A stands for anticlockwise, so is equal to, then again this is a C stands for clockwise. So in this equation I'm saying anticlockwise moment is equal to clockwise moment, and moment alone, M, is always found by force times the distance. All right, so that's what moment is. So this side you have to do force times distance, and this side also force times the distance. Okay, on this side of the pivot, and you have also this side of the pivot. So anticlockwise moment is when the pivot moves in the anticlockwise way, and then clockwise moment is when the pivot moves in the clockwise way, like that. Okay, so now we use this principle to find our force F here. So what we are going to do is this. So we'll get this force times its distance from the pivot. So this force here from its distance from the pivot, so times its force from the pivot. So I told you from here up to here it is 2 meters, because force times distance is the moment. So this force, its moment is this force, and the distance of this force from the pivot from here up to here. So this is a 4 meter wooden rod. From here up to here it's 4 meter. Now it has been pivoted on the middle, so from here up to here it is logically 2 meters. So you can put 2 there. Then we have another force here which is going through the pulley here. So this force is 20 newtons there. So despite it being there, we assume there's no friction here. So we assume the force that is transmitted here is the same force that is transmitted here. So we'll say plus. On this side, going this way, we have another force here. So say plus 20. So this force from here up to where? Up to the pivot, we have been provided 1.5. So say times 1.5, then plus, equals, we put this equal sign. Then we come this side. This side we have a 30 Newton force, then times the distance of this 30 from the pivot, which is 1 meters. Then another force here, we have it, so say plus. So another force is 20, then this 20 times its distance from the pivot. Again, from here up to here, you must understand that this should be 2 meters because it is from the middle up to the end. So 2 meters there. Then we'll say F times 2, it will just be 2F, then plus, then we'll say 20 times 1.5, it gave us 30. Then we'll put equals, then we'll say 30 times 1, it will be just 1, then plus 20 times 2, it will be 40. Now we want F, so we'll make it the subject of the formula by collecting like terms. So all these numbers which are constant will be on the right side of the equal sign. So this side will remain with this term which has got F. So here we'll have just F is equal to, so write 30 plus 14. So this one jumps on the other side. It is positive here. When it jumps, it becomes negative, like that. So when it comes negative like that, what we are going to do now is to say 30 plus 40, which is 70. 70 minus 30, it will be again 40. So say 2F is equal to 40. Now we are looking for F4, not to, so to get to find F, we need to get rid of the 2, so we divide by the 2 here, also here by the 2, so that F and F they will go. So have F is equal to 2 into 40, which will be 20 Newton. So our force is 20 Newton. However, when we check here, the answer is not there. I suppose that these guys made a mistake. So we are saying no answer, 3 mark. So in a case where there is no answer and markers try to answer the question and they verify that there's actually no answer, then they have to give you a 3 mark, because that is examiner's error. All right, now let's move to another question 4 here. They're saying the following picture shows children playing at a farm on a simple machine. Okay, this is a simple machine. If you can see it, like this one, we call it a seesaw. It is a seesaw here. This is a child, this is a child. Here it is a pivot, so they are swinging like up and down like that. Then the question says, what type of simple machine is this? So this one is just a lever. Let's not waste time. This is a lever. All right, so guys, if you're interested, if you're enjoying, give it a like and let me know also in the comment section. For those interested in online tuitions, if you're GCE or grade 12 internal, contact me on the number scrolling down there, 0977 92 41 75, so that you can join the online tuitions that I'm doing in science, biology, civic education, RE, maths, and English. All right, so let's move to another question, F5, which says the silver was on a thermos flask reduces heat loss by, okay, the silver was on a thermos flask reduces heat loss by, so those silver, they just reduce heat loss by radiation only, yeah, because by radiation. Otherwise it is not convection. Convection is the transfer of heat through fluids like air and then like liquids as well. Then conduction is the transfer of heat through solid materials where there is vibration of atoms getting in contact with each other. Electrons are moving and contacting each other, and in the process heat is being transferred. So radiation is never stopped. Radiation is a transfer of heat even through vacuum. Okay, so in a thermos flask, if you look at the structure of a thermal flask, except I didn't get that structure here, unfortunately, I'm sorry, I didn't put it here. It has double walls and a vacuum inside. That vacuum is just to stop heat transfer by conduction and then convection. Radiation passes even through vacuum. Now, to limit the movement of heat by radiation, you just have to make the walls silvery so that radiation can bounce back. So that's why the answer here is D. Then A6 is which substance P, Q, R, or S on the following table is a liquid at 20 degrees Celsius. Okay, so we have P, Q, R, S. Then they want us to see or choose the one that is going to be a liquid at 20 degrees Celsius. When we look at here, we have melting points and then we have boiling points. So if substances are melting here, they are melting so that they become liquids, right? Yeah. So that's what they will do. When they melt, they will become liquids. So if a substance melts at negative 218, it will become a liquid, and then starts boiling at negative 183. So meaning it will still, this one is still in negatives. It hasn't even gone to positives. It has already started becoming vapor, because it will be boiling now to become vapor. So no, by the time it goes to 20 degrees Celsius, it will be in vapor already. So this option is wrong. Then let's see Q at negative 39 degrees Celsius. It starts melting. Yes, it is melting. Then it will start boiling at positive 357 degrees Celsius. Yeah, so it can get up to that and then get up to that. As it melts, it can melt and then get up to that still in liquid form. Yes, then it will only start boiling at that. Yes, so this one makes sense. So this one is the correct answer. B. But this one seems to be, it will start melting at 39 degrees Celsius. Look, 39 is above actually 20. So meaning at 20 it is still in a solid because it is melting at 39. So this is not the option. This is again 44. 44 is already beyond 20. So at 44, let's say at 43, it is still in a solid. It hasn't actually melted. So the best answer is B. So we go to A7, which says the following diagram shows a transverse wave, which letter A, B, C, and D represents the amplitude. Okay, amplitude is the maximum displacement of a particle or wave from the equilibrium. This line represents the equilibrium to the crest or the trough. So the distance from here to there or from there to there is what we call the amplitude. So in this case, which one represents the amplitude? Not this one, not this one, not this one, but this one, C here. So C is our answer. All right, so guys, if you're enjoying, give it a like and also let me know in the comment section. Okay, liking videos like this helps YouTube promote this video in the algorithm to show to others that may want to benefit from it. Like some of you are seeing this video because someone liked it and YouTube had to push it also to you so that you find an opportunity to see it. So do also by liking it so that it can be pushed to others as well. All right, so we continue. So this is A8, which says which of the following waves is not an example of a transverse wave? You have A, infrared waves. Infrared waves are electromagnetic waves. Microwaves are electromagnetic waves. Then is radio waves are electromagnetic waves. Then spring waves must be longitudinal waves. So this is the answer here, because the question says which of the following waves is not an example of a transverse wave? Yeah, because microwaves are radio waves as well. Okay, yeah, so these are electromagnetic waves and are transverse waves. Then A9 says which of the following is not a use of ultrasonic sound? So ultrasonic sound is used in cleaning of machinery, echo sounding, yes, prenatal scanning, yes, treatment of cancer, no. We use actually X-rays maybe and gamma radiation to do such treatment like this. So this one is not a treatment or a use of ultrasonic sound. So the answer is D. Then we go to A10, which says which one of the following diagrams represents a ray of light moving from air into glass and out? Okay, so we have a glass block, glass block, glass block, glass block. So they want us to see the diagram which represents a ray of light moving from air into glass and out. Okay, so here you use a principle which says that when a ray of light moves from a less dense media to a more dense media, it refracts towards the normal. So in this case, there was no refraction, it went straight. If this is air, this is glass, it was supposed to bend towards the normal. Okay, so like here it bended towards the normal, and then when it emerged out of the glass block, it bended away from the normal, indicating that it had to speed up. So the correct one is this one here. Okay, then we go to 11A or A11, which says a ray of light travels from glass into air. The refractive index of this piece of glass is 1.5. Calculate the critical angle of this piece of glass. Okay, so critical angle is calculated using this formula, which says the refractive index is equal to 1 over sine C, which is C stands for critical angle. So what we can do is we can substitute N is the refractive index 1.5 equals 1 over sine critical angle. So we can also now make this one the subject of the formula by multiplying this times that. So okay, by swapping it will be like that, 1 over 1.5 like that. So this changing of the subject of the formula is in mathematics, because there was one that I saw commenting on my video asking how do you change the subject of the formula. No, guys, that is mathematics. If you want to know, then join my online tuition so that you can be taught that, because as we are solving here, we can teach how to do the changing of the subject of the formula. It is a topic on its own. You need to know different ways how we know how to change the subject of the formula. So this is how it can be changed as the subject of the formula. Then from there, we want still to make C the subject of the formula, but I did first the 1 over 1 divided by 1.5, I got 0.06666, something like that. Let me just show you what I got here so that you can appreciate what I'm talking about. So when I did 1 divided by 1.5, I got something like this one. So for the sake of space, I had to cut it somewhere here, 0.667 like that, okay, for the sake of space. Then from there we make C the subject of the formula, like C, which is critical angle, is going to be sine inverse 0.667. So when you do sine inverse of this, you are going to get a value of something like 42 degrees, or it will be 41.8, something like that, which I actually rounded off to 42 degrees Celsius to get the answer as A as the critical angle. Okay, again guys, for those that may be teachers and then they want to be preparing lessons for their pupils, learners like these, I'm using the Badcam as the screen recorder. So this screen recorder that I'm using, it is known as Badcam. It's a nice screen recorder. It is very light and then it is very affordable, so it is called the Bandicam. So the link is in the description. I'm going to leave the link there for this screen recorder so that you can be using it. Okay, it is very light and then it is versatile. Okay, so we proceed. So A12 says, which of the following diagrams shows magnetic field lines on two like north poles near each other? Which of the following diagrams shows magnetic field lines on two like north poles near each other? Okay, so remember, magnetic field lines, one of their properties is that they move from north to south. So they move from north to south. Like magnetic fields are supposed to move from north going to south, not like here. No. They're supposed to move like north to south, even here north to south. So this one becomes an answer, because when they say which of the following diagrams shows magnetic field lines on two like north poles, so these are like north poles. It is these. They're all moving from the north going to south. Here, no, this one is entering, then this one is moving, which makes it wrong. Here, this one is moving out. Here it is entering, which makes it wrong. The correct one is this one here. We move to A13, which says the following diagram shows two magnets L and M attracting 3 paper clips in between them. So you have this magnet and this magnet here, and they're attracting paper clips here in between them. Okay, then they're saying, what is the polarity at position P and Q of the clip and the magnet respectively? So polarity is the poles, north pole and the south pole. So they want us to indicate the polarity at P. What will be the pole at here P and then here at Q? So you know, this is magnetic induction being demonstrated here, the principle of magnetic induction. So for there to be attraction between this magnet and this clip, so this magnet induced some poles here. So if this is south, this was definitely north, and then the other side will be south. Then this will be north again, south, north, south, and then since they're attracting, this will be again north, this will be south. So P is north because this is south, north, south, north. So P should be north here, one of these. Then Q is south because it says north, south, north, south, north, south, north, south. So this Q is actually south, because north, south, north, south, north, south, north, south. Yeah, so the correct answer should be A there. So north, south. Yeah. Then we can move to another question here, which is A14. The following diagram shows a positively charged rod brought near the cap of a neutral electroscope. So in this diagram, we have a positively charged rod, which is this one here, that is being brought near the cap. This is the cap of a neutral electroscope. So this is the neutral electroscope with the metal cap here, the insulator, metal plate here, then the gold leaf here. Okay, then the question says what will be the charges on the metal cap, metal plate, and gold leaf. So they're asking what will be the charge here, and also charge here and charge here. So when this metal rod is brought near the metal cap, there will be electromagnetic induction that will happen, or electrostatic induction here. So when this one is brought near here, according to the law of according to the properties of electric charges, like charges will attract, and like charges will attract each other, while like charges will repel. So if this is positive, it has to attract the negative charges. So the negative charge, which is the electrons, will be attracted here, such that this part will be negative, and these guys here, they will remain with positive. So metal cap should be negative, so either this one or this one. Then this one should be positive, okay, and also this one should be positive. So the best answer should be B there. Okay, so A15 says, which of the following shows the correct color codes in electrical wiring? So this one actually, yeah, is something that I had to feel bad about it. Reason being is that the answers which were provided here ignored what we teach. They just looked at, okay, the good part is it matched some of the things we see in reality, but not all. Because a live wire here, they gave it a red either here. Then neutral, they gave it black. Then earth wire must be green. But neutral usually have blue, according to the theory I think we have. Yeah, but then that is fine. So the correct answer is B here. Okay, so live wire should be red, neutral black, then earth wire green. Unlike this option here, doesn't make sense. This is the only options which makes sense. So we go to A16. The following diagram shows a set of resistors connected in a circuit. So the following diagram shows a set of resistors connected in a circuit. So we have two in series. Again, this one are in series, but these and these are in parallel. And then we have a 3 volt battery source. Then we have an ammeter and a switch here. So they're saying how much current is recorded by the ammeter here when the switch is closed. When this switch is closed here, there will be current that will start flowing. So that current must be recorded by the ammeter. So what current is that? Well, this one we have to do some calculations, and this is why I hate multiple choice question. You see, these questions you have to do about 2 kind of calculations to arrive at the correct answer, but the mark that is awarded to this is just 1. So I don't know. So I think somehow the way the setting is done is not done squarely or fairly, because a question like this is given 1 mark when the calculations that one has to do to get the answer correct must be 2, because we have to resolve these 2 resistors must be added because they're in series, so they'll give us 4, and these ones are also in series, they'll give us 4. Now here we'll have 4 and 4, but the 4 here and the 4 here will be in parallel to each other, and then we need to find the total resistors by resolving the parallel resistors. So same resistor, total resistor here, it should be we'll consider maybe this one, resistor 1, which will be here, times resistor 2, which will be here, over again resistor 1 plus resistor 2. This is the formula for 2 resistors in parallel. Now, considering that here I've already added, I've gotten 1, which is 4, and here I've added, I've gotten 1, which is 4. So this one here, which is 4, we call it 1, and this one here, which is 4 as well, we give it 2. So say equals now, so get this one, it will be actually 4 times 4 over, again they are the same, 4 plus 4 there, which will be equal to 4 times 4, 16 over 4 plus 4, which is 8. Then we'll divide 16 divided by 8, which will be 2 ohms. Now once we find total resistor, then we'll find current using this formula. Voltage is equal to current times total resistance, the total resistance we have found here. So we are going now to make current the subject of the formula. Current is equal to voltage over total resistor. So we must calculate the current flowing here, which will be the current that the ammeter is going to read. So it will be equal to voltage 3 here, so divided by this is 3. I've put there total resistance, this one we have found, which is 2. So say 3 divided by 2, we are going to get 1.5 there as amps, which will be the current that will be read here. So the answer is going to be B. Now look at the solving here and the solving here, awarded 1 mark. So unfair. So anyway, let's move. So A17 says the following diagram shows an example of electromagnetic induction. All right, this is an interesting question. So we have magnet here with the south and north pole. Then we have an electromagnet here. Here is a solenoid or coil PQ, and then here we have a sensitive galvanometer. Then we are told which of the following set of information refers to the correct polarity of ends P and Q of the coil as the permanent magnet is pushed forward. Okay, when you push a magnet forward, this thing here, the coil also becomes magnetized and becomes a magnet. So the question is, what will be the pole here and what will be the pole here? So the pole which is introduced here is that which acts in opposition of this pole here, using Leslie's law, I think. Yeah, so the pole that is introduced here is the pole that opposes the movement of this pole here. So if we bring here, for what is going to oppose this one coming here, unless this one develops a north pole here, so that north pole and north pole will repel each other. So that tells us that this one will be north and the other one automatically becomes south. Now in the case where they are pulling this one here, right, if you pull this one here, so if this one is north as it is, right, and then you are pulling it the other way around, then this one is not going to be north, it will be south. The reason is the polarity that will develop here is that of trying to oppose this one going away. So if this one is going away, what is opposing it from going away, or for it to be opposed like from going away, it must be attracted. So the one that must be attracting it back, if you are trying to take it away, must be a south pole, because north and south must attract each other. So this is how these cases differ. So if you're pushing it this way, then this one should be north, so that the north behaves in a way as to oppose the movement of this one coming here. Okay, so I've explained the other one in another way, because in another exam they can bring a different situation where they're pulling this one the other way around. So in this case, this one is north, this one is south. So P should be north, but Q should be south here. So the answer is B. Yeah, so we move to A18, I mean. Which of the following best describes thermionic emission? It is the release of electron here by heated metal. Yeah, it is the release of electrons. So the answer is B. Then A19 says uranium 238, which is represented in this form nuclide notation, decays by emitting a beta particle to produce a daughter element with the symbol NP. Which equation represents the correct decay equation? Okay, so you know, when uranium, this one decay by emitting beta particle, a beta particle is just a fast moving electron, so it just emits a fast moving electron, meaning that when this one emits this a beta particle, which is an electron, then what will only happen is an electron has got a charge of -1 down there, and then it has 0 mass. So a decay equation becomes like this. So decay equation is this general equation I'm giving you here. If this one was a parent, and let's say it undergoes beta decay, so the daughter must be like this, plus this will be the beta particle. This is how we indicate the beta particle. So in that case, it means that if this is the symbol of the parent atom, this is its atomic mass. The atomic mass of the parent atom and the atomic mass of Y, this Y is the daughter element, must be the same. If this is A, this is A. They must be the same. Then this is the atomic number of the parent element. This Z plus 1 is the atomic number of the daughter element. So meaning the difference between the parent element and the daughter element is that the atomic number of the daughter is increased by 1. So in this case, let's pick this one. We start fixing here. Let's pick this one. This is 238.92 there. Then it goes there. Then the daughter, which is NP. Sorry, here I never put NP, I forgot, which is also not a problem. So meaning here we should also put it 238. But here we should add the 1 here as we add the 1 here. So to this we add the 1 to 92. It becomes 93. Then plus this here. So this is a daughter particle. So when you compare this one, these numbers are, it suits this one. This and this, it's this one. This, it is 238.93. 238.93. I said this one, don't mind, I forgot to change NP here. So we are just looking at these numbers here. And then this is 0, this is negative, correct, except this one put L there thinking it's E. This is E. L, the one who was typing doesn't know that this one is L, who was supposed to put E there. Okay, so the answer is in C. Then we move to A20. A20 says iodine 30, iodine 131 has a half-life of 8 days. If a sample of iodine 131 has an active of 600 counts, what will be the activity after 24 days? Okay, so here they are saying counts is what? Okay, so even they're asking here was or they said dash counts. Okay, the answer is dash counts. Okay, so the question is they want the counts. So for you to answer this question, you must either use this equation here, which is 2 to the power n is equal to A. This is activity, original activity over final activity. So if they are saying if a sample of iodine 131 has an activity of 600 counts, so this one is an original activity which represents A. Then they're saying what will be the activity after 24 hours. So that will be the final, which is A without anything here. So they want this one here. So to find this one, we make it the subject of the formula, which will be this over 2 to power n. N stands for number of decays that have passed. Now, we don't have n here, but we have this, we can put there, and then we need n there in order to find the answer. But n can be found from this equation, which says t, which is total time period, is equal to number of half-life over times half-life. So we make this n the subject of the formula, so it will be total time over half-life. So which will be equal to total time is this one here, where they are saying what will be the activity after 24 days. So T, which is total time 24 over half-life, is this one. They gave us 80 days. They says iodine 131 has a half-life of 8 days. So put it there. So say equals, so 24 divided by 8, it will be 3. So N is equal to 3. So say okay, equals now here activity original, which is 600 divided by 2 to power n2. N is 3. So N there is 3. So say equals 600 divided by yeah, the answer, I already found the answer there. Okay, I just found the answer fast. I never did like step by step there. So I just did like 2 to power 3, which will be 8. So I got okay, then 600 divided by 8, then it gave me 75. So that is the answer there, 75, that we are seeing there. So that will be the activity. So the answer will be A here. Now I had to also answer it the other way around, where you don't have to use these two ways. Again, this question again, you see it has a lot of work but 1 mark. So I had to find it another way, where you find it at once using this equation. Activity is final activity is original activity, open brackets 1 over 2 to the power T over T. Capital T is total time, small letter t is half-life. So we had to say equals, this is this 600, then open brackets 1 over 2 to the power T, capital is 24 there, total time, then T small letter is half-life, which is 8 there, then equals, then I had to say okay, this I had to say 8 into 24, which is 3, so to power 3. Then I had to say 600 is equal to, then it times, then I had to say 1 to power 3, it is 3 actually there, 1 to power 3. Okay, I had to just distribute this power, so 1 to power 3, and then 2 also to power 3. When then I said equals, then this one 1 to power 3, it will be just 1, then 2 to power 3, it will be 600 8, I mean, so it will be over 8. So like this one, 1 to power 3, it is 1 over 2 to power 3, it is 8. So 1 over 3, I mean 1 over 8 times 600, it gives you this. So say 600 divided by 8, you still get that answer 75, which we got there. Okay, so this is section A. It is done, guys. Let's give this video a like, and also let me know in the comment section, in case you have downloaded this video without giving it a like, go back to the channel, give it a like, and also let me know in the comment section. All right, because we are helping you guys, you can also help this video to go well, to do well in the algorithms. Okay, so we can also proceed to section B. So this is section B, where we have here 45 marks. So section B consists of 45 marks. They're saying answer all questions in this section, write your answers in the spaces provided in this question paper. So you write the answers in these spaces here. So B1 reads, figure B1.1 shows a stopwatch before and after it was used to measure a physical quantity. So this is a stopwatch. Before it was being measured to measure a physical quantity, it was pointing at that. Then after it was used to measure a physical quantity, it was pointing at that. Then A, they are saying, what physical quantity does the instrument measure? Oh, this instrument is a stopwatch. It is just a watch. What does a watch measure? Physical quantity, time. It's just time, like that. Then what type of error is shown on the instrument? Okay, before you start using it, this arrow is supposed to point at 60, which is the 0 mark as well. Now it is already pointing at somewhere. If I say this is 5, this is 10, then it's supposed to be 5, 6, 7, 8, 9, 10, 11. Okay, they also made a mistake here, but the fact is this is not pointing at 0, it is pointing at somewhere a number there even before it starts being used. So it has an error, and such an error where the instrument doesn't begin from 0 when you start using it, then that error is called zero error. So the type of error here is zero error. Okay, so let's move to the next question. So they're saying determine the error shown on the instrument. Okay, let me bring this one here. So determine the error shown on the instrument. So we have to read from here. If this is 60, we are supposed to say this is 5, then 6, 7, 8, 9, 10, 11. So this stopwatch which these guys drew is a wrong one. The correct one should be like this. Like from each point from this line to this line, you are supposed to have 4 lines, like 1, 2, 3, 4. But for these guys, they had to put 5. 1, 2, 3, 4, 5 before you find a long line. So they made an error there. Okay, I don't know how such a thing could happen where people can write such a stopwatch which had 5 lines in between. No, it's supposed to be 4 lines. So in that case, see, it made me, it was hard time for me to read, because it's supposed to be like 5, 6, 7, 8, 9, then you hit 10, then 11, 12, 13, 14, you hit 15, 16, 17, 18, 19, you hit 20. Okay, now here if you are like 5, then 6, 7, 8, 9, 10, 11. Where there's 10, there's 11. Wrong. So in such a case, it gave me hard time to see what error is here. So I had just to decide that it would be, if this is a 5, 6, 7, 8, where it is pointing there, I just had to put 8 seconds. Okay, then D, give the correct measurement of the quantity the instrument measures. So the correct measurement is, after they had used it to measure, it read this one here. So here, this is 35, 36, 37, 38. I had to take it that way. So for us to get the correct, we get 38 minus 8 here. So 38 minus this 8 here, which will give us what? 30 seconds. So this is the correct reading that was supposed to be there. Okay, so let's move to this B2, which says B2.1 is a speed time graph of an athlete in a training session. Okay, this is the speed time graph, where on the vertical axis we have speed in meters per second, and on the vertical axis we have time in seconds. Okay, so this is the graph. This is the initial velocity of an athlete to the final velocity, and then the velocity remains constant over this period from 5 seconds to 20 seconds there. So let's see the questions. The question says, what was the initial speed of the athlete? Okay, so this is just simple one. The initial one is supposed to be let me just go to where am I supposed to be. Yeah, so the initial one is supposed to be where he started from. So it is 3 meters per second. So the initial one is going to be 3 meters. Sorry, this is not where I am. So 3 meters per second. Okay, then they're saying, what was the maximum speed of the athlete? Okay, so the maximum speed of the athlete is this final speed here. So the athlete started from 3 meters per second, then went up to this. This is pointing at 5 meters per second, then maintained the same 5 meters per second here up to 20 seconds there. So the maximum speed is this. So we can just go there and say, sorry, and say 5 meters per second. Then C, they're saying calculate the uniform acceleration of the athlete. So acceleration is given by A is equal to final velocity minus initial velocity over time. So we'll say equals, final velocity is the same, this one, maximum 5 minus, then initial is this 3 we wrote here, over time. So we'll get back to find our time. So time now, will be time between 3 and 5 here where he reached maximum. So the time from here up to here, so from here where 3 is and to here where 5 is, from here to here the time is 5 seconds. So we'll go back, we'll say time here is 5 seconds. Then we'll say okay, 5 minus 3, which is 2. Okay, then divided 5, it will be that. So this is what I did there. First I said 5 minus 3, 2, then 2 divided by 5 there, and go to 0.4. So that's how I arrived at that. So that is 0.4. Now this is acceleration, it should be meters per second square. So uniform acceleration 0.4 meters per second squared there. So we move to D. They are saying calculate the total distance run by the earth rate. So total distance is given by, total distance is equal to area under the graph. So let's look at the area under the graph. So the area under the graph is just from here up to there. So the area under this graph here is going to be the total distance here, guys. So it will be equal to, if you check here, this graph can be cut into two. We can have this as a triangle and then this one as a rectangle. So the area of the rectangle becomes the distance, and then the area of the the area of the triangle becomes the distance, and then the area of the rectangle also becomes the distance. So we'll do it this way. So area of the triangle there, it is half base times height plus we have the area of the rectangle, which is length times breadth. So say equals we'll say half breadth times height. If we come here, you discover that from here up to here, this is base, which is from here it is 0.5. Again from here up to there, from here you consider this is 0, 1, 2, because the difference between 3 and 4 it's 1, and then the difference between 4 and 5 it is 1. So from here it is 1, here it is 0, then 1, 2. So from here up to here it's 5, from here up to there. Then from here up to there it is 2. So that's why we had to put a 2 here, then plus, then here we had 15 times 2 length times breadth. So we did this. So from here up to here it's the length, from here up to here it's breadth, which is 2. So from here up to here, so if from here 5, from here 10, so from here up to here it is 5. So here 5, then 10, then 15. So from here up to here it's 15, because or you can even say that from here up to here it is like, you say 20 minus we remove 5 here, we remain with 15 if you want. Then from here up to there it is 2, as I already indicated here. So this is why we had this part here. So everything, if you evaluate, you get 35 meters. So here to be 35 meters. Okay, then we come to this B3. Says figure B3.1 shows an experiment on heat showing different materials connected to a trough of boiling water. An equal amount of wax and a small metal pin is attached to each material as shown. Okay, so we have this is a trough, and inside there we are told there is boiling water, and then we have different materials. We have copper, we have aluminium, the first one, copper, then glass, then wood. Then here we have the pins here, and these pins are attached to these materials using wax. Okay, so here we are shown wax which is remaining, Okay, and then here we are told melted wax. Okay, so copper, this has melted wax, has melted, then all right, I think this wasn't really making sense, this part, just let's ignore it. Then they're saying identify the material where the pin will fall off first. Okay, if we are to follow this one, the material where the pin will fall first should be aluminium. But if we look at this experiment is testing which material conducts very well heat. So when we look at wood and glass, these are very poor conductors of heat. But when you look at copper and aluminium, you see that copper is a good conductor of heat than aluminium. So in such a situation, copper must conduct heat first, and then its spin must fall off first. And that's how I had to answer this question like that, copper. Now, however, when I look at again this time around, as I'm looking at it and reading the key correctly, it is as though the wax moved from this point up to there. They covered these things with wax up to there, and now the wax was melting, and then the white part is where the wax has already melted. So when you check for aluminium, this part here has melted more. It means if it continues, it will reach faster here for the pin to fall than for the copper, which has not melted largely. It still has a lot of wax remaining, meaning that copper will not, this will not melt faster for the pin to fall. So in that case, in this experiment, I think the correct answer here should have been aluminium, looking at the way I'm reading it now than I read it earlier on. Okay, so let's move. So again, what was the aim of this experiment? To investigate conductivity of heat by different materials. So that experiment is used to investigate the conductivity of heat by different materials. So see what can be concluded from the experiment. So from this experiment, we can say that the different materials conduct heat differently. Then in D, give one use of good conductors of heat. So in cooking utensils such as saucepans, we can use them also in boilers and so forth and so on. Then we move to B4. A says distinguish clearly between a transverse and longitudinal waves. So we can give a difference between longitudinal and transverse waves. So we can say that in transverse waves, particles vibrate perpendicularly to the direction of travel of the wave, while in longitudinal waves, particles vibrate parallel to the direction of travel of the wave. Yeah, that is a difference. Yeah. Then two, you either saying a round object is dropped in a pond of water. Describe the shape of waves produced in the pond. Okay, you get a round object, you drop it in a pond of water, then you see the waves will be in a circular form. So they are saying describe the shape of the waves produced in the pond. So we are saying the waves produced will be circular wave fronts spreading outwards from the point of disturbance here. That's what they are going to be. There will be circular wave fronts spreading outwards from the point of disturbance. When we say wave fronts, meaning they will be circle that will be equal in a distance from the point of disturbance. That's what we mean. Then 3, they're saying if a vibrator produces 20 ripples of water which passes through a point in 10 seconds, what is the number or what is the frequency of the waves? So we'll just use this one. Frequency must be equal to number of waves over time period. So we are told if a vibrator produces 20 ripples of water, that will be the number of waves. Then the time will be 10 seconds. So we'll just substitute there. So here we'll put 20 divided by 10, then which will be 2 here. So here will be frequency 2 Hz, like that. Okay. Then B, they're saying a boy standing in front of a building claps at intervals of 1 second. The echo produced coincides with the 5th subsequent clap. Calculate the distance between the boy and the building if the speed of sound in air is 340 meters per second. Okay, so in this case here, we are asked to find out a boy is clapping at an interval of 1 second. Maybe if he does one clap, for the second clap to take place, a time of 1 second passes, but then we are told the echo produced coincides with the 5th subsequent clap. So if he's clapping like 1, 2, 3, 4, 5, on the 5th one, the echo is heard. Okay, so if the echo is heard on the 5th one, it shows that 5 seconds had to pass, because if he claps 1 second passes, 2 another second passes, 3 another second passes, 4 another second passes, 5 another second passes, because we are told he's clapping at an interval of 1 second. So if he hears an echo on the 5th clap, that 5th clap coincides with the echo. It means that the time that has elapsed for the echo to be produced now is 5 seconds. So it's like the boy claps, so the sound goes to the building and then it comes back. Time elapses there, it's 5 seconds. Then they're saying calculate the distance between the boy and the building if the speed of sound in air is 340. So here it's just a matter of using this formula. Speed is equal to sorry, what happened here? Let me just control this stuff here. I'm really pissed off. Okay, so I said speed is equal to sorry, so this is what I was correcting. Unfortunately, in my animation of PowerPoint, this one came, it's like this one shifted here, so even when I've corrected it, it hasn't been corrected. So this equal sign will find it later. So speed is equal to distance over time. Then the question is saying calculate the distance, so make distance the subject of the formula. So distance is going to be speed times time, like that. Now here again, okay, so here distance is going to be speed times time. Now over 2, I've put over 2. This one is the same, I've put over 2, because this time which is here, which we are going to put here, which I've said 5 seconds already, is when someone claps, the clap goes, the sound of the clap goes to the wall and then comes back for someone to hear the echo. So if it goes and comes back, so in that same 5 seconds, the sound traveled twice. It had to go and come back. So for us to get the correct time, we have to divide that time by 2. That's why I've put these 2 here. Then we'll say, okay, equals speed, we'll put this one here, 340, then times the time, which is 5 seconds, over time t 2 here. The 5 seconds, if you see it here, is not coming, it's not appearing. It's what I told you, that if the person is clapping and per clap it is taking 1 second, and then he hears the echo after the 5th clap, then the time that has passed there also is 5 seconds. That is just using normal thinking. All right, remember, science, your thinking must be high there. If you are thinking very low in science, you are going to have problems. So when I'm teaching, I always tell my children or my pupils or my learners to say they have to tune the understanding volume high. So this one now, if we multiply everything, the answer is going to be 850 meters. So the answer is 850 meters there. So if you say 340 times 5 divided by 2, you get 850 meters there. Then we move to C. They're saying a vibrating tuning fork is marked 256 Hz. Calculate the wavelength of the sound wave that the tuning fork produces, taking the speed of sound in air as that shown in B4. Okay, the speed that was shown in B4 actually is what is 340. So they want the wavelength, and they have given us the frequency, which is 256 Hz. So the formula which connects these is this one here, where we say speed velocity is equal to wavelength times frequency. Now they want the wavelength to make it the subject of the formula. Wavelength is equal to velocity over time frequency. So substitute velocity. They told us we take that one which is in B4, which is 340 over, then frequency is going to be this one here, which is 456. So it is going to be 456 here. Okay, so which is going to be 340 divided by 456. It is going to be 1.3 meters as the wavelength. 1.3 meters there. Okay, then we come to B5 here. B5 says figure B5.1 shows a ray of light moving from medium A into medium B there. So we have a ray of light that is moving here from medium A here and going into medium B here, like that. Then A says define refraction of light. Refraction of light is just the bending. It is the bending of a ray of light as it passes from one medium to the other. That is what refraction is. So when a ray of light moves from one media to another, it bends. So that bending is what we call refraction. Then B, what medium is denser than the other? So between medium A here and this medium B here, which one is denser than the other? So the medium which is denser than the other is A. So we are saying medium A is denser than medium B. So they are saying justify your answer. We give a reason to our answer here. So let's give the reason to our answer. So let me just scroll to the point where we are in our answering here. So why we should justify that this one is an answer, is the correct one. So when you see, according to the way we teach, the way it is, if a ray bends away from the normal in the other media, like in this one, it has bended away from the normal, meaning medium B is less denser than medium A. That is actually the justification there. So we can say that this is because a ray of light has bended away from the normal as it merges in medium B. Then let's come to B6. Says figure B6.1 shows two bar magnets that are held close together. The polarity on one side of one of the magnets is shown by its symbol. Okay, so we have two magnets here, this magnet and this magnet, held together close to each other, and we are told this is the polarity south. Here here definitely it's north, but here we don't know, and here we don't know. But then they're saying when released, the magnets push away from each other. So these were held closer, but when someone stops holding them, these pushed each other, meaning this one went away and this one went away. Now, what can cause that? So since this is south, this is north. For this one to push away, it means this one was also north. Okay, so A, they are saying label the north pole on each magnet. So here it will be north, and here to be north. That's why there'll be that pushing, because like poles repel each other. Now B, they're saying write one word which describes what happens to the magnet as they are released. So when these magnets were released, they had to push away from each other. So they want one word that describes the pushing away. So that word is repulsion. Okay, that's what we say. So we go to B7A, which says what change is acquired by a material that loses electron by rubbing. Okay, when two materials are rubbed together and then one material loses electrons, then it will become positive because it will have excess electron. So this one will have positive charge because it will have excess protons, which are positively charged. Yeah. Then B, give one natural occurrence of static electricity. It's just lightning, guys. Then C, figure B7.1 shows a circuit. Okay, let me push it here. So figure B7.1 shows a circuit diagram with 3 different resistors connected to 24-volt supply. So we have this resistor, this one and this one, they are connected to the 24-volt supply, and then we have an ammeter here. Then they're saying A, define resistance. Resistance, it is the opposition to the flow of electric current in a circuit. That is the resistance. Then yeah, so part 2, they're saying calculate the total resistance in the circuit. Okay, so we need to calculate the total resistance in this circuit here. So total resistance is first of all found by calculating the total resistance in parallel, then add it to that in series. So this is what we are going to do. So let's find total resistance in parallel first here. So this is it, I brought it here. So in parallel, we'll use this formula, total resistance in parallel. So resistor in P means parallel. It will be, let's say this is resistor 1, this is resistor 2. So it will be resistor 1 times resistor 2, again over resistor 1 plus resistor 2. Then we'll substitute parallel resistor is equal to resistor 1, this is 3, then times resistor 2, which is 6 here, then over, then resistor 1 is still 3 here, plus resistor 2 is still 6 here. Then we'll say equals 3 times 6, 18 over 3 plus 2, which is 8. 3 plus 6, which is 9. Then there we'll say equals 18 divided by 9, which will be 2 ohms. So now this is just resistor in parallel. Now we have this one here. So total resistor, now we should add the resistor in parallel plus the resistor in series. So RP, this one in parallel, RS, this one in series. So we'll just add this one in parallel is 2 plus this one in series, which is again 2. So we have 2 again, what we found here, which is this. So 2 plus 2, it will be 4 ohms. So here the answer will be 4 ohms. Okay. Then 2, they're saying 3, what is the current in the circuit? So like they want what current is in this circuit here. So current should be found using voltage and total resistance, which is this here. So say we'll use Ohm's law, which says voltage is equal to current times total resistor. Then we'll make current the subject of the formula. So current, you see, so this is the equation like the one I showed you in section A. In section A, we solved this one and we solved this one. Here you see 2 marks, 2 marks, 4 marks for 1 mark which was given in section A. This is why you heard me saying it is very unfair, because in section A we had a similar question where we solved twice total resistor and then we used the total resistor to find the current, just like this one. But here 2 marks, here 2 marks, you have seen. So I don't know, examiners, they are very, very unfair for how they allocate marks. Anyway, we continue. So making a current the subject of the formula, to be this one here, which is voltage over total resistor. So equals voltage is this one here, 24, divided by total resistor, which is this one we have found here, 4. Oh, sorry. So okay, so I had to make a mistake here, sorry. So let me just see how I should have now found here. So it should be 24 divided by 4, which was going to be 6. So in my calculation area, I had to put 2 here. Because of this error of putting 2, I got 12 volts, and I mean 12 amps, and here I had to put 12 amps. But is that the correct answer? No. The correct answer is 6 amps here. So put 6 amps here, guys. Okay. Thank you so much. So let's move to another question. Question B8 says figure B8.1 shows a simple diagram of a transformer. So this is a transformer input output. A1 says what type of a transformer is shown in figure B8.1. Okay, this type of a transformer where you have more coils on the primary coil and less coils on the secondary coil, it is called a step down transformer. So this one is a step down transformer. Justify your answer. A reason is the one I've said, that because it has less turns in the secondary coil than the primary coil. Yeah. Then B, they're saying give 2 ways in which the efficiency of a transformer can be improved. The number 1 way is by using large turns in the coils by using large wires in the coils to reduce resistance in the circuit or in the coil. Yeah. So large wires, if they are used here, then there will be reduced resistance, then efficiency will be more. Then also by using a soft iron core to reduce hysteresis losses. So if you use a soft iron core around this, it reduces the hysteresis losses, which is the demagnetization and the magnetization process. So if these are reduced, then you expect the efficiency of a magnet to be more. All right, so let's push to the other one. B9 A sees the table. B9.1 shows some of the results of a comparison among alpha particles, beta particles, and Y rays or gamma rays. Complete the table by filling in the missing properties. Okay, so we have particles, we have these here, alpha, beta, gamma. Then in nature, here we are told these are alpha are actually nuclide. Yeah, they are helium nuclide. Then a charge, you see here the charge here, we are told it is actually positive 2. If we come to beta, we have to put ourselves here, and here gamma, we put ourselves. So in terms of nature, gamma are just electrons. Okay. Then in terms of charge, gamma have got a negative charge, -1 unit. Okay. In terms of gamma here, beta electrons, that is their nature. In terms of charge, they have got a -1 unit. In terms of gamma rays, their nature are electromagnetic waves. These are electromagnetic waves. Then their charge, they have actually 0 charge. It is actually 0. So let's push this one a bit here. So they're saying figure B9.2 shows 3 radiation or radiative emissions, E, F, and G from a radioactive substance directed at 3 different substances. Okay, we have this, and that. We have this radiation E, F, G. They're directed here: paper, aluminium, and lead. So they're saying identify the emission E, F, and G. So this property is just about the penetration power. So this one, which has less penetration, is alpha, then alpha particles. Then this one, which is a bit more, which is penetrates through paper but is stopped by aluminium, it is beta particles. But this one, which penetrates through the paper, aluminium, and it can penetrate also lead, or it can only be stopped by lead. This one is actually gamma rays. Okay, so that is that. Then we move to this one. Give one difference between E and G. So E is alpha, then G is gamma. So one difference is that for these is that alpha particles have weak penetration power, while gamma rays have strong penetration power. Yeah, so we move to the other one, section C, 20 marks. So here we are told to say answer any two questions from this section in the separate answer booklets provided. So here they give you 3 questions, then you answer only 2. Each question that you answer carries 20 marks. So C1 says table C1.1 shows a force N and acceleration meters per second of a box recorded while being pulled along a horizontal surface by a learner. So force, these are the forces, then acceleration, that is the acceleration, then A, define force, B, state Newton's first law of motion, then C, plot on a graph paper a graph of force against the acceleration, then D, determine the gradient of the graph, then E, what physical quantity does the gradient represent, then F, from the graph determine the force that produced an acceleration of 3.5 meters per second. Okay, so in answering we have to define a force. Okay, that's what we have seen here. So we have to define what a force is. So let me just scroll to that point. We are defining a force. So we are saying a force is a pull or push. That's what we can define. If we want, just put a force is a pull or push. If not, same, a force is that which tend to change the object's state of rest or uniform motion. Yeah, so a force can either be defined by this one or the second one. Okay, then we go to B. What does B say here? B says state Newton's second law of motion. Okay, so I think I had to put a wrong one here. Yeah, I had to put the first law of motion here. That's when I've remembered. So let me give you the first law of motion. I mean the second law. This one which is here is wrong. The first law of motion says that an acceleration of an object is directly proportional to the force that produces it and inversely proportional to the mass. So the acceleration of an object is directly proportional to the force that produces it and inversely proportional to the mass, meaning acceleration is equal to force over mass. That is the second law. So second law of motion of the second law of Newton's motion says that the acceleration of an object, or let me put it in this way, it states that unbalanced forces acting on an object produces an acceleration which is directly proportional to the force and inversely proportional to the mass. Okay, so Newton's first law of motion states that unbalanced forces acting on an object produces an acceleration which is directly proportional to the force and inversely proportional to the mass. Yeah, so the one I've put here is wrong. Okay, I didn't realize that it was the first law I'm putting here. Okay, then let's see the other question. The other question says plot a graph of force against acceleration. Okay, let's do that. So I had to come here, see, I brought a graph here, So we have to plot a graph of acceleration. I had to put acceleration, force against acceleration. I hope this is visible. So here, if they say force against acceleration, meaning acceleration should be on the vertical axis, then force on the acceleration on the horizontal axis, force on the vertical axis. Okay, then we can put our line here and then the line there, and we can get our data here in this table, because this is the data we are going to use to plot. So what is now remaining is to ensure that we spread this data in what they call the scale factor of the graph. Yeah, though they don't mark it, but the scale of the graph can be generated from here. I never indicated here when I was typing, so I will not indicate it right now because I'm already in motion. So you ensure that the values you put here on the vertical axis are those that will accommodate this, and then the values that you put on the horizontal axis are the ones that will accommodate this. So on the horizontal axis, it's not effective in difficulty. Here you start with 0, then here you put 1, 2, 3, 4, 5. That's what I had to put. So if we have to look at the scale, this box here represents 2 centimeters. That's what it is. So according to the scale, if you wanted to write it, you can say x-axis it is 1 centimeter is equal to 1 unit. That's what you can say here. 2 centimeters is 1 unit. Now on the vertical axis, it was quite tricky for me. So I had to look at 0 0.2, 0 0.5, 0 0.7, then 1, then 1.25. So I had to decide that from here to here I give it 1, then from here to here I give it a 2. So that when plotting, I will be saying that here 0, 0, I put a point there, then 1, 0.25, 1, 0. So this is 1, so this is 1, so these are 10 of them, 20 of them. So here it should be 0 0.1, 0 0.2, then 25 in the middle. So I said 0 0.1, 1, 0 0.1, 0 0.2, 0 0.25 should have been there, but I had to round off to 3. So I rounded this to 3, this part here. So it is now 3 here. So this is, let's see, 1, 2, 3. Yeah, 0 0.1, 0 0.2, 0 0.3. Yeah, I think that is how I did it. Then 2, 0 0.5. So here I'm at 2. So I said 1, 2, 3, 4, 5 there. Then here 3.7. I think this had also to go to 8 if not mistaken. So if this is 5, 6, 7, 8 somewhere, there are 0 0.6, 0 0.7. I think I should have put it there. Anyway, no problem guys, it doesn't make a mistake. Maybe this was also shifting. That's how I have changes. Then 4.1. So this is 4.1 is there. Okay, I think here there was just a minor error. Then 5, 1.25. So 5, here 1.25 somewhere there. Okay, so this is 1, 1 here, 1.1, 1.2, 1.3. Okay, here I rounded off to 1.3. It's just here where I made an error. So this one I did not round off. I think this one is the one I did not round off here. It should have gone there as well. So once you do that, you draw a straight line. So you have seen, so it has passed through those lines nicely like that. So here I said 1, 1, 2, 3. Okay, so this is a straight line. Now when making a straight line, it should pass through the points. So when you see it has passed through the points, no, you go for what we call the base fit, but should pass through the origin and any other points here. So on the upper side we have remained with it 2 points where it has not touched. On the lower side there's at least a point, and it has gone through this point, and this point. So this graph is okay as it is. Then we go to the other part. This other part says we have plotted this, then determine the gradient of the graph. So we'll now determine the gradient of the graph. So gradient D, gradient M is equal to change in Y over change in X. So this triangle means change in Y, change in X. So this is the Y axis, this is the X axis. So what we do, we choose any 2 points which are lying on the straight line, like this point is lying on the straight line and this point here. Say equals, so at this point we'll get this value, which is 1 minus, then this point we come here. So if this is 0, this should be 0.51, 1.52. So here I went on the y-axis, I get a 1, which is that one, then minus. I come on this one, I go on the y-axis here, I get a 0.5, then I say over, then I come now here again on the same point, I come on the x-axis, I get a 4 because it corresponds to 4, minus, I come on the same one here, I go to the x-axis, I get a 2, so I'll get a 2 there, and I say 1 minus 1.5 is 0.5, then divided by 2. So what I did, I already found the answer. This is the gradient, in fact. So I did 1 like that. I did like 1 minus 1.5, which I got 1 minus 0.5, I got 0.5, then I said 4 minus 2, 2, then 2 into 0.5 there, I got 0.25 there as the gradient. So this gradient here, I never gave it the units, but you can give it the units as force over meters per second square. Okay, then E, let's look at the other one here. So when you look at E, they're saying what physical quantity does the gradient represent? So that gradient which we found there, the physical quantity it represents under E, it is actually mass. Then we go to the other question, which is F, from the graph determine the force that produces an acceleration of 3.5 meters per second. So come to the graph. So come at 3.5 here. This is 4, this is 3, middle here, it is 3.5. You draw a line here. When it reaches the graph, you follow that line here. So this line where it touches here, it is actually at 0.85. That's what I had to put, because if this is 1, 0.5, then 0.6, 0.7, 0.8, then 0.85 Newton. That will be the force at 3.5 meters per second. The force will be that. So that's how you find that one. Then let's see if we are done. I think we are done. So we can go to the next one, which is C2. Says table C2.1 shows result of temperature in degrees Celsius against current in millimeter amps obtained when a thermocouple thermometer was calculated by immersing the cold junction in pure melting ice at 0 degrees Celsius, and the hot junction placed in water of different temperatures. So this is the result on this table here. Then A, they're saying plot a graph of temperature in degrees Celsius against current in millimeter amps. Okay, so this is what we would do there, right? Okay, so we are plotting a graph on 2A. Bring a graph of temperature against current. So that's what we are going to do. So we drew here. So here we had to put current in milliamps, then here temperature in degrees Celsius. So this is what we have to plot. So here again, we ensure that the information for the current fits nicely here. So we have 0, 0, 1, 2, 3, 4, 5, I think. So I did like 0 here, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. I think I ended on 0 0.5 here. So this information will fit very well here. Again, for information that will fit here, I said, okay, this will be 25, 50, 75, 100, 125. So this will also fit nicely there. Then I started now plotting like 0, 0, it will be a point there. Then I had also 0 0.1, 25, so 0 0.1, 25 here, and then 0 0.2, 50, 0 0.2, 50 somewhere there. Then 0. This one I had actually to round it off to, no, I never rounded it off. This is 0.29. So this is 0.2 here, 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. So 0.29 is here, 75. So 75 somewhere there. That's how I took it. Then here 0.4, 100, 0.4, 100 there, and then 0.5, 125. So 0.5, 125, which is there. Then I had to draw a straight line like that. That's all. Okay. Then oh, these I never animated them again. What the hell is this? So where are we now? How have I gone back to this? Yeah, so B1, we are told using the graph determine 1, temperature of the hot junction when current is 0.35. Okay, that's where that other thing is coming from. So here current is 0.35 is here. So I drew a line. I never animated them, I forgot, and then it landed on that one there. So where it landed here, that's where there was B1. Where it landed there, it was 87.5 degrees Celsius. How I got that one was I actually did, if from here to here it is 25, right? And there are 10 units there. So I had to do some mathematical calculations to know how much each line represents. So I said, okay, 25, if I were to divide it by 10, I got a 2.5, meaning from here, one line stands for 2.5. So now here, if you see the harmony 1, 2, 3, 4, 5, 5. So 2.5 times 5, you get harmony, you get 12.5. So 12.5, you add on 75 plus 75, you get something like 87.5. That's how I arrived at 87.5. That will be the temperature there when that will be the temperature when the current is 0.35 milliamps. Then 2, they're saying current that will flow when the temperature of the hot junction is 333 Kelvin. So this question again was not supposed to have 2 marks. It was supposed to have 3 marks because the work needed to find this one is more than this, because temperature has been given in Kelvin, so you need to change it in degrees Celsius for you now to go on the graph to find the current that will be equivalent to that temperature. So I don't know why they did that, but let's answer. So they are on 2. This is the formula for changing temperature. So this is temperature in degrees Celsius is temperature in Kelvin minus 273.15. So here temperature in degrees Celsius is 3.33 Kelvin. Oh, here it's supposed to be K. What happened? Okay, K. So the 3K minus 275, and the answer was 60 degrees Celsius. So you come on 60, which is somewhere here. This is 2.5. So 60 will be somewhere here, because from here to here 2.5, and from here this is 2.5. This is okay, 50, 52.5, 55, then is 75.5, then is 60. So 60, you run there, you come down there on the current. So this is 0 0.2, 0.3, 0.4, 0.5, 0.6. So 0.26. So the current, whoa, I made a mistake again. Sure. So it is not, because I did 0 0.2, 0.3, 0.4, 0.5, 0.6. Damn, what did I do? The correct one is 0 0.1234. So 0. Okay, 1, 2, 3, 4. No. So I said, I counted from there, which is wrong. It's supposed to be 0 0.24. So there's a 2 missing here, 0 0.24 milliamps. So maybe it could have been a typing error where I missed a 2 there. So 0 0.24 milliamps. Then let's check for the other question, which says state the physical quantity a thermometer uses to measure temperature. That is actually current. So that physical quantity is actually electric current. Then the other question says give one advantage of a thermocouple over a liquid in glass thermometer. So here we said rapid response to temperature change. Yeah, so a thermocouple has rapid response to temperature change than a liquid in glass thermometer. Okay, so let's go to the last question, which is C3. They're saying a home has a television set rated 14 watts that is used for 10 hours a day, a hot water geyser rated 4000 watts used for 3 hours a day, and a cooker rated 2000 watts used for 2 hours a day, all connected in parallel to a 240 volt power supply. Draw a circuit diagram to show how 3 appliances are connected. Okay, so we draw a circuit diagram. They're in parallel, so it will be like this. 2A. So this is a 240 supply. Oh shit, this 240 supply should be an AC one. So an AC one, we don't do it like this. Yeah. It's supposed to be something like this. Wow. Also speed cues, huh? Because typing takes time, so I was typing fast for me to finish this one. So this one, I was supposed to do it like this. A point there and a point there, and then just write something like this to show that it is AC. Wow. Sorry, because I started typing this at night and then completed it today, so meaning I was just fast. So yeah, so that fast speed cues again. Speed cues. So let's do that. So let's move on to B. So if we check B, they're saying use the graph to determine. No, I've already gone back. How have I gone back? B, calculate the power used by 3 appliances. So the power, this one is 40 watts, this one is 4000 watts, this one is 2000 watts. So we just add it. So to find the total power is equal to the one for 40 watts plus 4000 watts plus 2000 watts, which gives us 6040 watts. This is the total power. So power is added like we add numbers, whether in series or in parallel circuit. Then we come to see if electricity costs 20 ngwes or 20 ngwe per kilowatt hour. Calculate the cost of using these 3 appliances in a day, 3 months. Okay, so cost now will be equal to, cost of electricity should be equal to electric energy times unit cost. So you need to know electric energy times unit cost, then you get the cost itself. So here you say equals electric energy is always given by power times time, then times this unit cost. Then power, this power should be converted in kilowatts. So this power is always converted in kilowatts. So let me get the calculator. So this power, total power, which is this one here, 640, must be converted to kilowatts. That's how it is. So by dividing by 1000, that's how it is. So it will be 6.04. So time is 24 hours because we are told, let me just show you, we are told that in calculate the cost of using these 3 appliances in a day. So a day has 24 hours, so that will be the time there, 24 hours. So here we'll use this on power, which is 6.04 times time, 24, times unit cost. Unit cost, we were told it is 20 ngwe. So if we multiply everything here, we should be getting 2899.2 ngwe. So that is what we are getting there as our answer. Then we go to the other one, if I have not made a mistake, guys. Then we go to D. D, we are told that calculate the electrical energy used by the television set in the period stated in C. So in 24 hours, we want to find the electrical energy used by the television set. So we'll get back, we'll say electrical energy is equal to power times time. So this electrical energy, power is actually 0.04. I've changed it, okay, because when you check here, calculate the electrical energy used by television. So the television is using 40 watts. So that 40 watts, I changed it to kilowatts. So 40, change it into kilowatts by dividing by 1000, which gave me 0.04. So that is what I did there, so that you don't get confused. Then come back there. Time is still 24. So if we get this one times 24, it is going to give us 0.96. So the units here then, since this power we have used it is in kilowatts, and then time is in hours, so it will be equal to 0.96 kilowatts hour. So this is correct, but you can convert it in joules by converting it in seconds and to time, but this is how I had to find it. Then in the last question, I think, which is suggest a fuse D, calculate the electrical energy used by television set in the stated period. Then E, suggest a fuse rating suitable for the geyser. 1 mark. This question never demanded 1, it was supposed to have 2. So this is a geyser with 4,000 watts. So now what they want is the rating, like the type of the fuse that it will use. For us to know the type of the fuse this geyser can use, we need to find its current. So so we needed to calculate its current. So then after we calculate its current, then we can now suggest the fuse to use. That's why it needed 2 marks, because you cannot know the fuse rating without calculating for current. So you are answering 2 questions, but they are given 1 mark. So these examiners, they are mad. Yeah, that's what I can say. They are mad. They are very mad. So yeah, you see, they are mad. So let me just answer it. So first of all, we say power is equal to voltage times current, or current times voltage. So we make current the subject of the formula, power over voltage. Then we know that the power for the geyser is 4,000 watts over, then the voltage is 240. When we divide this, we get 17 amps. I just rounded it off. I got like something like 4,000 divided by 240. I got something like that, 16.7. So I rounded it off to 17. Now for us to know the fuse now that must be used for this current, the fuse that must be used must be a little bit larger than the current that it should allow to flow. So we cannot put a 17 fuse or 18 fuse. Like the fuses I've seen, some are 2 amps, some are 3, but then they go to 5, 10, 15, and 20. I think that's what I've seen. So this one, the fuse that should be used should be 20. So we can say the fuse rating should be 20 amps. Yeah, so that's how we should have answered this question. So we have come to the end of this science paper. If you enjoyed it, give it a like, and then subscribe to the channel for more videos, and then let me know in the comment section. Thank you for watching us for now. Bye, and see you in the next video. Peace.